Hello. All right. Okay, guys. So today we're going to be looking at this lesson here that you see here, which is all about something called number sets. And to start that, we've got this little YouTube video here, and we're going to watch it together. So let's try that.
Natural numbers, whole numbers, integers, rational. In this lesson, we're going to be learning about the different classification of numbers, which include natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. So the most basic type of classification of numbers are the natural numbers, and this is a symbol that we use to represent them. Natural numbers include numbers such as 1, 2, 3, 4, 5, and so on. They are often referred to as counting numbers. Now, natural numbers do not include 0 or any negative numbers, as well as any decimals. So, an easy way to remember this is to think of it like this. We all naturally count things starting from 1 and go on to 2, 3, 4, 5, 6, and so forth. But rarely do we count starting from 0. Therefore, this is the innermost basic classification of numbers. The next layer of numbers are the whole numbers. Whole numbers can often be denoted using this symbol. Now, the classification of whole numbers are exactly like natural numbers, in that it includes all of the natural numbers and it also includes 0. So instead of starting from 1, whole numbers start from 0. Another cool way to remember this is to think about it like this. Whole numbers are exactly the same as natural numbers, except that they start with a number that looks like a whole. Therefore, whole numbers include natural numbers, and this means that any natural number is also considered a whole number, but not necessarily the other way around, since 0 is not a natural number. Do note, however, that the classification of these two are still a little bit hazy, as some places might teach you that natural numbers do in fact include 0, disregarding the classification of whole numbers entirely. It is common to see that in set theory or in computer science, since in these fields they actually do count starting from 0. But for the sake of this video, we're just going to include the classification of whole numbers as well. The next classification of numbers is something you are likely to have heard of before. They're called integers. Integers can often be denoted using this symbol. Integers include all the same numbers as whole numbers, like 0, 1, 2, 3, etc. Except they also include all the negatives of them as well, such as -1, -2, -3, -4, and so on. But again, integers do not include decimals or fractions of numbers. The next classification of numbers are called rational numbers, which can be denoted using this symbol. And again, rational numbers encompass all of the other classification that we've mentioned so far, as well as decimals and fractions. However, the decimal numbers must be numbers that can be expressed as a fraction, where p and q are integers, and q is not 0. So, for example, 17 over 3 is equal to 5.666 repeating, and since the numerator and denominator are both integers, this is in fact considered a rational number. Now, whereas this looks fairly organized with its repeating sixes, even something like 19 over 17, which yields this rather unpredictable looking decimal, would still be considered a rational number. And why? Because this is an integer, and this is also an integer that is not equal to 0. Okay, so far so good. So if I told you that I'm thinking of a number and that it is a natural number. Can you assume that this number is also a rational number? Well, definitely. You can also assume that it's a whole number since that's a bigger set. You can even assume that it's also an integer, since it's an even bigger set than that of a whole number. And finally, as we mentioned, you can also assume that it's a rational number, since rational numbers are a bigger set than the set of integers. We can compare it to something like this. If I said that there's a person in Tokyo, can we also assume that this person is in Japan? Well, obviously. As well, would we be correct to assume that this person is also in Asia? Absolutely, since Tokyo is in Japan and because Japan is in Asia. And finally, would it be okay to assume that this person is on Earth? Well, of course, because Earth is even bigger of a set than Asia. Good. Now, there's a whole different set of numbers that is not within any of these. This set of numbers cannot be expressed as a fraction. Another way to describe this is that this set is completely separate from the rational numbers altogether. Fittingly so, we can call these numbers irrational numbers. An example of an irrational number would be pi. And we know that pi is a never-ending number that does not repeat with a constant decimal or in a pattern fashion. And this is what makes it irrational. Square root of 2 also turns out to be an irrational number, since it cannot be expressed as a fraction. And lastly, the definition of real numbers is the last classification that we'll talk about. Although there are some other classifications that you might learn later on down the road. Real numbers are simply all of the rational and irrational numbers combined. So pay close attention to how certain number sets are literally in the other sets. But just remember that even though saying that a person in Tokyo must also be in Japan is correct, the reverse isn't always correct. If this person is in Japan, it doesn't necessarily mean that they are in Tokyo. Maybe they're in Osaka or wherever else in Japan. Similarly, while we can say, for example, that all natural numbers are also integers, we cannot say that all integers are natural numbers. The same applies to the rest of the layers of classifications that we've learned. So, the classification of numbers might seem random, but they will be used over and over again, so it'll be well worth your time to learn it thoroughly right away.
All right, well, that was enthralling. Um, if we take a look at this, we can kind of use that to fill out this note, and hopefully that'll help us to understand what we're looking at here. Oh, that's not what I meant to do. Sorry about that. Okay, so what we can then say is that this whole box here, this whole thing represents what we call the real numbers, right? And the real numbers literally contain every number that is real. But then within that, we've got the different layers, right? So we said we've got the natural numbers, n, and then outside of that, we have what we call the whole numbers, right? And that's this box here. And then outside of that, we've got what we call the integers. And again, we're going to define all these on the side, but we're just kind of laying out where they fit. And then finally, outside of that, we've got kind of two distinct sections. We've got what we call the rational numbers, which we denote with the letter Q. And we've got what we call the irrational numbers, which we denote with the letter P. All right, so there we go. That's kind of the layout. Now let's remind ourselves what each of these means. When we talk about the natural numbers, we're talking about 1, 2, 3, 4, 5, and so on and so forth. Goes on forever. Right, so natural numbers are those kind of natural numbers that we naturally count with. The whole numbers fall right in that same kind of category. The only difference with them is, just like it said in the video, that these include now the number 0. 0, 1, 2, 3, 4, 5, ... And then outside of that, we have the integers. And just like the video said, the only difference there is that we accept negative numbers too. -5, -4, and sorry, I shouldn't, that implies it starts at -5, but we'll do ... to show we could have -643 if we wanted. I'm going to stop at 2 because I'm out of room, but the idea here is that we are counting. And keep in mind here, all three of these have in common that there are no decimals and no fractions. Right? And then when we get outside of that, we can get Q, which now would have, say, -2, but you could also have -3/2, -1, 0, 1, 3/2, 2, ... And now we allow fractions and decimals. In fact, instead of saying -1, I'm going to say -1.2 instead of saying +3/2. Or sorry, instead of saying +1, I'll say 1.2, just to show that here you can have decimals and you can have fractions, and that's okay. And then the irrational numbers are a whole different thing, because here we can't have 0 or 1 or 3/2 or 1.5, nothing like that. What we could have is, and we couldn't have, say, the square root of 4, because the square root of 4 is just 2. But what we could have is the square root of 3, or I guess I'll put that in bracket. We could have the square root of 3, or we could have the square root of 29, or we could have the number pi, or any of these things, any number that can't be expressed as a rational number, can't be expressed as a fraction of integers. So that's our number set. So now, let's take a look at what we can do with that. And to do that, I'm going to get a calculator, and you're going to need a calculator. So let's make sure we have one. And hopefully there's a set of calculators in the room. If there's not, we can go across the hall to Mr. Calford's room, if somebody could run across and get them, and just make sure we have a set of calculators. So let's look, and let's try putting these numbers on the number line. Let's start with the square root of 49. Now, when we go to take the square root of a number, it might be an irrational number. We have to check. If it doesn't work out nicely, it could be irrational or not. So let's take a look and see if we can figure out what the square root of 49 equals. And all we have to do that is we could take the square root using our calculator. And to do that, on this calculator, I press that second function button, and I press the square root button. So second function, square root right there, and then 49. And if you know your perfect squares, you know that the square root of 49 is just equal to 7. So we can actually take that and we can put it right here on the number line. I'm going to put it right above. I'm going to say that's where the square root of 49 goes. Take a minute, pause this video, and see if you can get the rest of those points put here on the number line. And if you want to use some highlighters, if that helps, there's highlighters on the side of the room. But pause the video now. Try and get these on and help each other out. Math's a team sport. All right, so I'll assume you paused the video and tried. Let's take this up and see how you did. So this next one is negative 58 over 7. And of course, that's a fraction. And this number line doesn't have fractions over 7 on it. So let's see if we can figure out what that number is. So on my calculator here, I can press that negative button down here, and then I could do 58. And over 7 is another way of saying divided by 7. So the fraction negative 58 over 7 equals this big long decimal. It equals negative 8.2857, and that keeps going. But here's the deal. We know that that's still a rational number because we know it started out as a fraction. Anyway, let's put that on the number line. And 8.28, well, that's between 8 and 9. That's maybe about there. So I'm just going to put a mark there, and then we'll say that that is negative 58 over 7. All right, hopefully you got that. Let's try the next one. The number 8 kind of goes without saying. I shouldn't need to mark that too much. So we'll just put that there, and we'll say that. Oh, but not negative 8. It's positive 8. We'll put that right there, number 8. All right, let's try the next one, negative 7 over 3. And now we're back to another one where I don't necessarily know off the top of my head where that should go because it's a fraction. So again, I can come to my calculator. And on this calculator, if you try to use the subtraction button for negative, it'll say answer minus because it thinks you're trying to do subtraction. So you have to use that negative button right down here. So we'll press that, negative 7. And then over is another way of saying divided by. In fact, if you look on the calculator here, it shows it that way. And that is negative 2.33333. I'm going to mark that down here, negative 2.333. So let's mark that here. That's about there. We can write that down as negative 7 over 3. Okay, let's try the next one. So this one here, negative square root of 56. Again, I don't know off the top of my head what the square root of 56 is, but we can do it on the calculator. Press the negative button. Second function down here, second function x squared, if you look, has that square root symbol, and we can take the square root of 56. And that doesn't work out nicely. This one's actually an irrational number, and that's okay, because we can still put it on the number line. It should be negative 7.483 dot dot dot. So we will take that and we'll put it here. Negative 7.4 would put it right about there. And that was negative square root of 56. All right, negative 6.5. I should be able to put on without having to do any calculator work. That's just going to be right there. Negative 6.5. And same with 2.4. That's pretty self-explanatory. We should just be able to put it on. Round about there. So take a moment, check that against your work, and see how you did. Note that when we go to put these on, it's really helpful to use the calculator to figure out what those numbers are, sort of expressed as a decimal value. That's going to help us with a number line because we're used to thinking of numbers on number line as decimal values. Okay, I want you to pause this video again and take 2 minutes and see if you can answer A and B here, which is where you're trying to put these from least to greatest. And then once you feel like we've got a feeling on that, come back. All right. Let's have a couple people answer it out. Now, I obviously can't actually hear what you say, but I'd love to know kind of what people thought here. And this has a few things going on. It's got a mixed number going on, this or that, but let's see if we can work these out. So 5, we don't really need to do anything with because we know what that number is. 4 and 3/5, well, we know that that's got to be less than 5, right? Because it's 4 and a bit. So I think if we're going from least to greatest, I'm going to put 5 here. And then I know that 4 and 3/5 has to be less than that. If I want to know what that exactly was as a decimal, I could do 4 plus 3/5, and my calculator would tell me that that is 4.6. If we want to kind of continue doing that thing where we look at things as decimals. Okay, what about square root of 36? Now maybe you know that, which is great, but if you don't, no problem. We can come here to the calculator. And again, if we press that second function button and then the x squared button on here, it gives us a square root, and we can take the square root of 36. And when we do that, we get 6. Right? And that is bigger than 5, so we can put that here. And that leaves us just with 19 divided by 4. And again, maybe you can do that in your head, but if you can't, come here on our calculator and we can say 19 divided by 4, 19 over 4. And that as a decimal is 4.75. And 4.75 is less than 5, but it's bigger than 4 and 3/5. So I'm going to come over here. I'm actually going to erase that 4 and 3/5. And I'm going to put 19/4 here. I'm going to put 4 and 3/5 there. And in the end, that should be the order of those numbers from the smallest one to the biggest one. And just to remind us what they were, this was 4.75, this is 5, that's 6, and this we said was 4.6. So that's the order there. Again, see how putting it as a decimal can help. Let's see how you did with this one here. So again, 14 is already a decimal. Let's do 91 over 6 and see what that is as a decimal. And I get 15.16666, and so on and so forth. And sometimes we put this little bar over a number to show that that number just keeps repeating. We already know what 14 is. Square root of 210, we can just take here and take the square root of 210. And I get 14.49, and it keeps going. And then finally, 51 divided by 4, we can do the same thing. And I get 12.75. So that means if we're going with the smallest number, 12.75 is the smallest number, right? So it'd go 12.75 is the smallest, and then 14, and then 14.49, then 15.16667, right? And so now if I put those numbers in as we originally had them, 12.75 was 51 over 4. This one was just 14. This one was the square root of 210. That means what number times itself equals 210. And that's 14.4913567. And lastly, 91 sixths, or 91 divided by 6. That looks like a 7. Let's try again. Cool. All right. Hopefully that made some kind of sense to you. Hopefully you did well with that. So now there's just a little bit of practice here where we want you to go through and from all of these sets of numbers, see if you can find subsets and see if you can find lists of numbers that come from them. So again, I want you to pause this video and see if you can fill all of these in and talk to each other, help each other out. We'll do just the first one together. List the set of natural numbers less than or equal to 11. So if we go up and look and we said the natural numbers start at 1 and they just keep going up always by 1. In other words, just counting from 1. So if we want all the natural numbers that are less than or equal to 11, well, that would be the natural numbers n, and again, they start at 1, and then 2, and then 3, 4, 5. We have to get to 11. I'm writing too big. Let's try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, pause this video. You try the next bunch. All right, we're back. So let's take a look. Whole numbers. Well, if we remember the whole numbers, denoted W, they go 0, 1, 2, and they just keep counting. And we want the ones that are less than 8. So 0's less than 8, 1's less than 8, 2, 3, 4, 5, 6, and 7 are less than 8. And then what about 8 itself? Do we include that? Well, 8 isn't less than 8, so this would stop at 7. If you got that, give yourself a big pat on the back. If you didn't, just blame, I don't know, I like to blame Trush for things. You can blame Trush, it's okay, I won't tell him. What are the similarities and differences between the natural and whole number sets? Well, really, the only difference is 0. The naturals include it, and 0 is not a whole number, right? So we include 0 in the natural numbers, but we say it doesn't belong. Oh, sorry, I literally said that backwards. We said it doesn't belong in the natural numbers, but it does belong in the whole numbers. All the even integers from -4 to -2. Do we know what even numbers are? If not, that's okay. Even numbers are ones that are divisible by 2. So from 0, we'd say 2, 4, 6, 8, dot, dot, dot. And on the negative side, -2, -4, -6, -8. And so, which ones go from -4 to +2? Well, -4, -2, 0, and 2. And 0 is considered an even number, so we can put it there. List the set of all integers that are multiples of 3. Well, that would start at 0, and we'd go up by 3, 6, 9, 12. And obviously, we're not going to keep going forever, because that would take forever. But remember, integers can be positive or negative. So this would also be -3, -6, -9, and that would also go on forever. So in both directions, -12, -15, -18. What are the differences between the whole numbers and the integers? Negative numbers, right? So the whole numbers don't have them, but the integers do. And any way you want to say that's fine, but integers have negative numbers, whole numbers don't. Right, create 4 subsets of this set. Not a lot of room to do this here, really, in this handout, is there? Okay, I'm going to create a subset. And the first one, I'm just going to put -8 in. There's a subset. I'm going to make another subset, and I'm going to put -7, -5, and -3 in it. I'm going to make another subset that only has -5 in it. And then I'm going to make another subset that has -8 and has -3, and that's it. So those are my 4 subsets. There's no right answer. You could even make a subset of these that has no numbers in it. It's kind of weird, but that actually would satisfy that subset. You can make a subset that had all of them. That would still be considered a subset. Colin says there's a total of 7 subsets in this. Well, your subsets could be 1, 2, and 3. That's a subset of it, even though it's the same. Just 1, just 2, just 3, 1 and 2, 1 and 3, 2 and 3. So that's 1, 2, 3, 4, 5, 6, 7. I would make the argument that an empty set is also a subset of it. I'd have to ask Mr. Kelford what he thought of that, but I think that actually would be true. So yes, or 8 if we count an empty set. And the empty set is sometimes called the null set. How are integers related to rational numbers? Well, rational numbers can be fractions, but it has to be integer over integer. So that's the relationship. So again, there's more than one way to say that, and talk to each other. You may have answered some of these questions in a different way that was still a right way. Just because you don't answer it the same way I do doesn't mean your answer isn't correct. And if you're not sure if your answer is correct, normally I'd have you just put your hand up and show me, and I'd come around and take a look. But since I'm not here, talk to the other people in the class, discuss it, see if you think you agree or don't. And I'll certainly be happy to take a look at that when I get back to school in a couple of days. Anyway, that's it for the lesson part of this, and I hope that made some kind of sense to you. And there's some practice on the next page, and I want you to do all the ones that are circled. Try it out. If you have questions, talk to each other. If talking to each other doesn't help, feel free to send me a message. I'm here to help, and I will see you guys on Monday. Have a wonderful weekend. Have a wonderful day. Use your time well. Make sure you put this stuff into your notebooks and that your notebooks are nice and neat. All right, we'll see you Monday. Bye.